Hey everyone, and welcome to The Explainer. Today, we're diving into a truly paradigm-shifting approach to software architecture and clean code. We are going to look at how we can fundamentally change the way we handle data in our programs. We're moving away from those fragile, error-prone habits that keep us all awake debugging at 2 a.m., and we're stepping right into the world of mathematically proven, rock-solid code.
So I want you to think about something for a second. Have you ever accidentally swapped two arguments in a function call simply because they were both strings? Let's be honest, we have all been there, and it is such a painful, time-consuming mistake to track down. Blindly trusting a caller to pass valid data in the exact right order is a massive, widespread habit in software development, and frankly, it's a habit we urgently need to break.
Here is our roadmap for today. 1. The primitive obsession problem. 2. Refactoring to custom types. 3. Building smart constructors. 4. Parse-dont-validate explained. And 5. Proving it with types. Let's get into it.
Section 1. The primitive obsession problem.
Okay, so in programming, we're all pretty familiar with the idea of replacing magic numbers, those unexplained raw numbers just floating in our code, with meaningful named constants. We do it because it makes the code readable, right? Well, there is a very similar issue that totally flies under the radar for a lot of developers, and it's called primitive obsession. This is a recognized code smell where your code relies on basic primitive data types, like strings or integers, to represent really complex domain objects. Basically, instead of modeling our actual business domain, we lazily lean on built-in primitives. Let's look at exactly what this vulnerability looks like in practice. Take a look at this Haskell function signature. We've got a send email function that takes 2 arguments and returns a result. But notice the types here: string, arrow, string, arrow, string. It takes an email as a string, an address as a string, and returns a string. Because this function accepts multiple primitives of the exact same type, it makes it incredibly easy to accidentally pass invalid data, or, even worse, completely swap the argument positions without realizing it. When this actually happens in production, the fallout is incredibly frustrating. Because both arguments are just strings, your compiler is not going to warn you if you swap them. It sees a string where a string is expected, and it just gives you the green light. Plus, any operations related to that data, like your formatting or your validation logic, end up scattered all over the place in generic utility functions rather than living cohesively on the type itself. Ultimately, this just creates a really weak domain model. Your code ends up communicating technical data types to the next developer, rather than the actual business domain concepts. It just makes it so much harder to reason about what the code is actually supposed to be doing. Section 2. Refactoring to custom types. Now, notice the stark difference here. This is where we fix the problem. We are physically changing our code from a weak domain model that relies on raw strings into a strongly typed custom data model. So instead of send email taking a string and a string, our strong model takes an email type and an address type. Suddenly, just by reading the signature, the business logic is absolutely crystal clear.
Now, you might be thinking, okay, but what about performance? Creating all these custom wrapper types sounds kind of heavy. Well, here's the beautiful part. In Haskell, we can mitigate primitive obsession with absolutely zero runtime overhead by using the new type wrapper. By defining new type email equals email string, we create a distinct dedicated domain type for our email, and we can do the exact same thing for our address. At compile time, the compiler treats them as strict, entirely distinct types, but at runtime, they are just strings, costing us absolutely nothing in performance. It's a total freebie.
Section 3. Building smart constructors.
So we have our types, but we don't just want to blindly wrap any random string into our brand new email type. We need to enforce some rules. Enter the smart constructor. Take our mkEmail function, for example. It takes a string and it checks if the @ symbol is actually present. If it is, it safely wraps the string in our email type and returns just email string. If it isn't, it returns nothing. We are enforcing our validation rules right at the moment of creation. Think of it exactly like a cryptographic ID badge. You literally cannot get the badge if you don't pass the background check. The old way was basically like handing out unverified guest passes to anyone who walked up and asked.
And similarly, we can build a smart constructor for our address type. The mkAddress constructor simply ensures that the address string is not empty. If the string isn't null, it wraps our data safely into the custom address type, returning just. Otherwise, it returns nothing. Now, by forcing the return type to be a maybe, we are forcing absolutely any developer who uses this function to explicitly handle the possibility of failure right up front. There's no sweeping it under the rug.
Section 4. Parse-dont-validate explained.
This quote right here completely encapsulates the entire parse-don't-validate paradigm. Refuse to hold unvalidated data in standard primitives and use the type system to guarantee that invalid states are unrepresentable. I really want to emphasize this core philosophy. By completely preventing invalid states from even existing within our type data structures, we fundamentally shift our entire mindset. We are transitioning from merely hoping the data is right and having to check it constantly to physically proving it once and for all.
What's really fascinating is when you directly contrast these two approaches. In traditional validation, you're operating on raw primitives and your checks happen repeatedly throughout the entire execution of your program. But look at the parse-don't-validate approach. We parse those raw strings into typed domain models. Notice how this new approach moves the checks to exactly once, right at the system boundary, just like we saw in our smart constructors. The proof of validity isn't scattered in a bunch of runtime Boolean checks. It is encoded permanently into the Haskell type system. The downstream guarantee is absolute. Your function physically cannot compile without valid types.
Section 5. Proving it with types.
So how do we actually use our new, robust types? We can use pattern matching. In this snippet, we call our smart constructors mkEmail and mkAddress. Because they return a maybe type, we use a case statement to handle the result. If and only if we get just email and just address, we proceed to actually call send email. The beauty of this is that our send email domain function safely unwraps these types, and it never ever has to recheck the data. If it receives an email and an address type, the data is guaranteed to be valid. The compiler has already proven it for us.
And hey, if you want to see some truly elegant syntax, we can achieve the exact same safe execution using applicative functors. Just look at this gorgeous one-liner. Send email, $bracket, mkEmail, $, asterisk bracket, mkAddress, $. Using those $bracket and asterisk bracket operators, Haskell smoothly handles the entire maybe context for us behind the scenes. It will only attempt to apply send email if both smart constructors succeed. This is just a brilliant demonstration of Haskell's zero overhead safety, which gives us clean, concise, and incredibly robust code.
So let's sum this up. What are our ultimate downstream guarantees by utilizing parse-don't-validate? Well, our code now operates exclusively on strong domain models, not weak primitives. Our validation checks happen exactly once, right at the system boundary where the data first enters. Because of this, our downstream functions physically cannot compile if you try to pass them invalid data or if you try to swap the arguments. Ultimately, the mathematical proof of your data's validity is encoded directly into the type system itself.
I want to leave you with this final provocative thought. If your compiler can mathematically prove your data is valid, why are you still just validating? It's time to challenge the old habits. Stop relying on scattered, easily forgotten Boolean checks. Start leveraging your type system to parse data properly, make those invalid states unrepresentable, and transform the way you write robust software. Thank you so much for joining me on this explainer, and I highly encourage you to start experimenting with these concepts in your own codebases right away. Catch you next time.